Okay, because sometimes I forget and I should record another lecture. And I know students like to feel being in the class, not just have a lecture. Okay. So now I'm recording, and this is like the attendance slide. So when you're working on this, I just talk about like my stories. So those of you who took, quiz 1 makeup and also homework makeups, you know that the printer had some issues. So I printed lots of extra makeup quiz 1 and some, extra makeup homework 3. So I didn't have like enough to bring to the class and distribute to the class, and I didn't want to hand in some of them to students. I'm going to upload them on Canvas, so don't worry about them. But if you're willing to also have a physical copy, I have them available, so just stop by my office hours or my office anytime and pick them up. Any questions? And as I said, I'm going to post them on Canvas today along with the study guide that I'm going to write for your exam, which kind of like prepares you. And if you can answer all the homework problems, quiz 1 and quiz 2, and also the makeups that I'm going to post on Canvas, I think you'll do really well on your exam, honestly. These questions would be really similar. And that's one of the good things about like giving you 20 questions for each homework, because even if I want to ask you anything new, it would be really similar to the homework problems. Especially the makeups, I know some students, they just don't go to Canvas to study new materials. Even some students don't go back to see what was the right answer to their homework problem or like quiz problem. So I really encourage you to study those, because it sucks if you come to the exam and then realize that 10 out of 25 questions were exactly the same questions that you had in your quizzes or exams, or like all of them. You might see almost the same questions. Okay, so I don't say that I purely ask from those resources, because I'm going to design some new questions. I'm not going to just copy from them. But you see that we have like HF, NH3, H2O, that they form like hydrogen bonding. So if I want to ask another question, so in one question I may ask, does HCl have hydrogen bonding? And you'll see that lots of the questions are really similar, because the examples that I provided in the class are kind of like limited, and I'm not going to ask you any trick questions. Okay, any questions before I proceed with the lecture? Good? Everyone is good with the attendance? And the other thing, last night I had to enter early warning grades, and I spent lots of time for my Chem 101 class to count the attendance, and there were like much more students in that, so many more students in that class. So it took me lots of time, so I couldn't count the attendance for 275. So for that matter, I only entered grades, not the attendance. But hopefully this weekend, I'm going to count all the attendance. So most of the time, students that I see on a regular basis are students who show up to the class. So basically now my audience is mostly students that are not in the class, so I'm recording the lecture for them. So I'm going to send individual flags in Vandalstar about attendance for CHEM275 to individuals who don't attend the class. Okay, any questions, concerns? So before I proceed with the lecture and talk about like reactions of alkanes, do any of you have any questions or any concerns about any of the topics that we covered so far that you want me to explain more or like have an example? Anyone? Yes?
Can we talk about constitutional isomers just a little bit?
Yes, of course. Let me find my, where did I put the, Let me just find the pen. Did it just disappear on me? I'm sure I put the pen here. Okay, here. I was like, did it just disappear? I was always telling my classes, law of conservation of mass, things don't disappear. But several times I see things disappearing on me and then I find them later. Anyway, so we want to talk about constitutional isomers. So let me write an example and explain that. So structural, how your book says that different bond isomers, they have the same bonding pattern. So if I write them on the paper, they even seem the same. But when I look at them in the space, in the 3D structures, they are different. So they have different arrangements in the space. Does that make sense? But the bonding pattern, so for like, stereoisomers or conformational configurations, we have like the same bonding pattern. But in this space, the atoms have different configurations or conformations. Is it clear now? Yeah, thank you for asking that. And I'm going to ask you in the exam on Friday about like these terminologies. And again, when I repeat these things, it will be just like reading basically. Structural is the same as constitutional. Remember that. So it's kind of like just like repeat those, so remember. And the other thing that is important, interconvertible was here too. So this is the correct way of writing this, right? You probably know better than the book. Anyway, so yes.
If it's not interconvertible, that means the bonds have to be broken in order to correct them.
Exactly. So for conformational or conformers or rotamers, all of them are like, the same, have the same meaning. So for those, if, you have like a structure in the space and then around one bond, you rotate the molecule, again, you don't change the bonding pattern. Bonding pattern is the same for both of them. So if you have like carbon attached to oxygen for both isomers here for conformational and also configurational, if carbon is attached to oxygen, in the other isomer is also carbon attached to oxygen. But here, for stereoisomers, and imagine like conformational, if carbon is attached to oxygen, the other isomer is also carbon attached to oxygen. But when you look at them in the space, like cis and trans, right? Cis and trans are like, configurational that you cannot interconvert them, right? But rather, regardless, if you have like carbon attached to hydrogen in cis, right? Remember, in cis, we have like are both, branch in the same side of the ring. Remember? So for like, I'm talking about like stereoisomers in general. If carbon is attached to hydrogen, in trans also carbon attached to hydrogen. But in a space, they have different arrangement. And as your friend mentioned, if, in conformational, if I rotate the molecule in space around a particular bond, I can get the other structure. So by single bond rotation, I can convert one to the other. But for cis and trans, for instance, or in general configurational isomers, I cannot get one structure, the other isomer, by rotating that molecule in space. Yes?
So for the interconvertible, do you expect us to be able to like find the other isomer, like if you turn it?
Exactly. So depending on, for instance, for the ethane, we had like several examples, right? Remember, your book had like so many different pictures. And depending on around which bond you rotate the molecule, you can get the other structure. But for configurational, you can't. And again, your book has lots of examples about like, rotate this molecule by 60 degrees to get the other structure, those things, so I'm not going to ask you that. As long as you know the concepts, the definitions, and knowing like staggered eclipse for ethane, and knowing that staggered has the lowest energy, is the most stable one, and why eclipse is not stable because of steric interactions, and also knowing cis and trans are like, configurational isomers. It means that you cannot interconvert them by single bond rotation. You will be fine. Does that make sense? So I expect you to know the materials, the concepts, but I'm not going to ask specific about conformational isomers.
One more. So,
Yeah.
sec-butyl, tert-butyl, and isobutyl, are those conformational isomers or are those just structural?
Those are structural because they have also different bonding patterns, right? And I have like, let me, if I show you, do all of you know that which section in book we had like isobutyl? Let me go to DocCam. And for people watching this at home, I'm showing, I guess for my books, page 42, which is like 2,4 alkyl and halogen substituents. So you see, for instance, here you have like for sec-butyl, and this is like a good point, that your friend asked, because I'm going to ask that in your exam. So remember, and you have like similar question in your quiz too, that you're asked to write different, alkyl groups. So remember, here you have like, for instance, if just comparing like isobutane, with butane itself, where do we have butane? Okay, if we want to write butane, can anyone tell me how to write that? If I want to write butane, what is the formula for butane? C4H10. Remember CnH2n plus 2, right? Good. So if you want to write that, you have like 4 carbons. Remember, in alkanes, you can have like a chain of carbons. What did we call this? Catenation, right? So, and then you see how many hydrogen you're missing. And remember, what is the valence of carbon? 4, right? Okay, so for people who are watching this at home, I just like wrote the structure of butane, and I missed this one. So you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or you can write this CH3, CH2, CH2, CH3, right? And now look at this structure, isobutane. And these are like structural isomers. You see that how we have like in isobutane, we have 1, 2, 3, 4 carbons attached to each other. You see the difference here compared to here? And the same thing for their isomers. And I'm going to, because I'm going to ask that in the exam, I'm going to switch to the HDMI so I can also write this here. So again, to kind of like demonstrate the point, here we have like butane. Did it just change the screen kind of like, or did I just, yeah, I was like, did I imagine that? Or did it happen? Anyway, this is a side effect of running so much, sometimes you black out. Anyway, so now isobutane. So this is isobutane. We have like 4 carbons attached with each other like this, and then you count, the valence of carbon is 4, so you have like 1 carbon bond, 3 more here, 3 hydrogen here, 3 hydrogen here. How many here? 1, right? So these are structural isomers or constitutional. Okay? And the same thing for their alkyl groups, right? So we write, let me write here. So basically butyls. We have like 2 of them, basically N, we call that, N-butyl, because it's kind of like, we call that, the normal alkanes that we have like the long chain, we call them N-butane or like N alkanes in general. So if you see like your book just says like butyl, but it's the same as like N-butyl, okay? Or butyl. And also sec-butyl. These are derived from, I guess I write here. These are written based on N-butane. So based on this. Okay? So how we write these is the following. So when you want to write, butyl, if, can you guys see this, or is it too small? I want to have like, the N-butane here. If you just drop 1 hydrogen here, if you drop 1 hydrogen here, you get CH3, CH2, CH2, CH2. So this is butyl or N-butyl. Okay, so you just drop 1 hydrogen here. Any questions? Or if you drop a hydrogen from the second carbon here, we'll be getting like exactly sec-butyl. So we write CH3, CH, CH2, CH3. Does that make sense? So you don't even have to, kind of memorize the structures, so without any rules or regulations rather. Yes?
So sec means second carbon?
Yes.
Oh, great.
And now if we look at isobutane, so the other 2 that I'm going to talk about, isobutyl and basically tertiary butyl, they are taken from like isobutane. So if I drop the hydrogen, for instance, here, if I drop like 1 of these hydrogen, for instance this one, and the structure that your book wrote, I guess I write this with blue, you have like CH, CH3, CH3, CH2. And you see that, it's kind of like, if you consider this, if you just like rotate it, is like basically this part, right? Can you see that? If you just like, this is structure. I don't think if I can. Yeah, unfortunately I cannot just like rotate this to the degree I want. But if you have like this structure there, CH, CH3, CH3, imagine if I just like bring it here. Can you see that? Mm-hmm. Kind of like 45 degrees. If I just rotate it, I have here, and I drop 1 hydrogen here. It would be this structure. Can everyone see that? Yes?
What is the intention of the additional bonding line on the furthest side?
It just wants to show you that it's just like part of another structure.
Okay.
Right? For instance, when you have like the substituents in like alkanes or like cycloalkanes, or like in general, the naming of the alkanes that we were doing, you have like a methyl group, you also can have a butyl group, right? We mostly talked about like ethyls, methyls, like 1 and 1, 1 dimethyl, right? Or like when we were naming, remember? So we didn't talk about butyls a lot, but technically they are part of another structure. So that's why, your book wants to remind you that, carbon has a valence of 4. It already has like, 2 bonds here, 1 bond here. So it should be having another bond. So kind of remind you of that. Great question. Any other questions? Okay, so are we good with isobutyl? So remember, if you have the carbons like a chain, you have, normal butane, N-butane, or like butane. If you have carbons kind of like bonded together like this, you have isobutane. And also the isomers, when you're writing isomers of butyl, if they are like, you see carbons attached to each other like this, and they are not a straight chain, you know that you have alkyl group derived from isobutane. Does that make sense? And remember, N-butyl, or like butyl itself, and 6-butyl, they are derived from N-butane, but isobutyl and tert-butyl, which is taken from like tertiary, that's how you say it, they are like taken from isobutane. Are we clear? And let me write tert-butyl as well. So in this structure, if we drop like this hydrogen here, we get tert-butyl. Let me change the color because that color is too bright, I think. Okay, so CH3, C, CH3, CH3. So basically I just dropped this hydrogen. That would be tert-butyl. Are we clear? At least remember, yes.
So for the isobutyl, why is it kind of at an angle, but tert-butyl is? Oh, never mind. I see my mistake. Never mind.
Okay.
Yeah.
Any questions, concerns? So again, I kind of like emphasize this because I gave you a whole question in your quiz, and I'm going to ask that in the exam. So basically, as long as you learn this, you should be fine to answer the question. Great questions. Any questions about this or any part? Yeah.
I guess, how do I know that that's the hydrogen I have to drop in the tert-butyl?
This is just how scientists agreed on this. Kind of like, are you Amy?
So just memory.
Yes. Yeah. But yeah, this is the thing about like organic chemistry. There are lots of things to memorize. So I try to make it like to the point that you can rationalize things and then memorize with the rationale, I guess, rather than just like repeating something to remember. But bottom line, we should just like remember that if the structure is like this, it's like butane. If it had carbons like attached like these, this is isobutane, kind of like, and then we have like tert-butyl and isobutyl taken from isobutane. Okay, any other concept that you want me to emphasize or like write an example before I progress with the lecture? Oh, yes?
Can we go over solubility real quick, like briefly?
Okay, and what did you want to mention? Hydrogen bonding solubility, great. Oh, so I write hydrogen bonding and solubility. I mean, I kind of love this, that students ask questions and then I go through the material. Sometimes, in my like other class, I ask the students, any questions? Nobody responds, I say, do you have any, concerns, anything? And then, sometimes I ask students, how many of you think this, how many of you think that? And nobody raised their hands, they're just waiting for the class. So I appreciate, the course participation. So first, let's talk about like hydrogen bonding because I just wrote it first, but I'm going to cover both. So hydrogen bonding is type of intermolecular forces. And in this course, we talk about intermolecular hydrogen bonding. So intermolecular forces, I guess I review this real quick. So we have like hydrogen bonding, we have dipole, and I couldn't catch up with these lines, and London dispersion or van der Waals interactions. So in general, remember. So something to remember is that hydrogen bonding is also type of dipole. Okay? So if I tell you which of the following the compounds don't have dipole as their intermolecular forces. Even if you see something that has hydrogen bonding, technically it has dipole. Okay, so you should choose the one that has London dispersion. Does that make sense? So this is kind of one thing to remember. And dipole in general, you know, dipole London dispersion, they relate to electronegativity. Negativity of elements and also their geometry, which means like distance between charge separation. Remember the example of CO2. So you compare electronegativity of carbon and oxygen, and each bond itself is polar. And do you remember polar bonds? That polar bonds are bonds that electrons are not shared equally between the atoms. Sometimes, you know, you see not, and then you think that maybe it should be non-polar. That's not the case. And remember, you know, we talked about like polar molecules. Pole in general, it means that we have like positive and negative. So one atom should be slightly positive, the other should be slightly negative. They should be having like different electronegativities. Can anyone tell me what was electronegativity? Yes?
The want of an atom to draw electrons in.
Exactly, the tendency of atoms to, you know, attract or absorb electrons towards themselves, right? So when they do that, they have like slightly negative charge because electrons have negative charge, and the other atom would be having a slightly positive charge. So these bonds are polar individually, but you remember that we would write an arrow towards a more electronegative element, and when you write these arrows, they cancel each other. So this molecule is non-polar, the molecule. The bonds are polar, but the molecule is non-polar because of the arrangement of charge, or like charge separation. And we have like some slides on that, so if you have like difficulties, refer to them, ask me questions and all that. But right now, know, you know, that for the sake of your exams, CO2 is not polar or non-polar, right? CH4, remember carbon, hydrogen have similar electronegativity, so alkanes are non-polar, is non-polar. And these are like the same, okay? C2H6, C3H8, right? So all of these are, I guess it didn't save me that much time, is non-polar, is non-polar. If you have like the same element, N2, O2, F2, these are non-polar. So all of these have London dispersion, exactly. Okay? So this is kind of like a tricky thing because students think that CO2 has polar bonds, so it's a polar molecule, but it's not because of the arrangement of charges or like electronegativity, how the atoms are like arranged as we wrote here. Any questions? So dipole is like atoms. Basically, most of the things, most of the molecules would be, if you don't see like a diatomic molecule or like alkanes or like CO2, most of the time we'll be having like polar molecules. So some of the examples would be like HCl. As I said, even hydrogen bondings, these have hydrogen bonds, but they are also dipole. Or like BF3, lots of examples, right? So these are like dipole. And now, going to the question that your friend asked about hydrogen bonding. Hydrogen bonding, first of all, remember, is intermolecular force. So it's not between like nitrogen atom and then hydrogen atom of the same molecule. It's not what we're talking about in this course. It would be between the molecules. So, and it should be between nitrogen, oxygen, fluorine that are attached to hydrogen, okay, from one molecule, and hydrogen that is attached to nitrogen, oxygen, fluorine of the other molecule. So for instance, hydrogen in HF and oxygen in H2O, right? Or hydrogen in HF and fluorine in HF, right? Or NH3, nitrogen in NH3 and hydrogen in fluorine, right? But it cannot be between nitrogen in NH3 and hydrogen in HBr. These two don't have hydrogen bonding. Is that clear? Any questions about hydrogen bonding? Okay, so now going to solubility, if there is no question. Remember, for solubility, like dissolves like, meaning that if you have like a compound that has dipole, it dissolves another compound, that has dipole interactions between them. Or if you have like London dispersion, it dissolves another compound that has, I'm just like copying from what I wrote above, London dispersion, okay? So you look at the interactions. If you have hydrogen bonding or dipole interactions between them, and you have for the other molecule also dipole or hydrogen bonding, they dissolve in each other. But if you have London dispersion in one molecule, and for your other substance you have hydrogen bonding, they won't dissolve. So if I ask you, does CO2 dissolve in water? No. These are having like different. This is London. This is hydrogen bonding or dipole, right? So they're not. If I ask you CH4 and water, again, this is London, this is hydrogen bonding or dipole. If I ask you NH3 and water, they do, right? Or if I ask you BF3 and water, right? Both of them dipole or hydrogen. If I ask you BF3 and NH3, yes, right? So as long as you know that like dissolves like, you know, you can answer this. Any other question that I go through it in 1 minute? Or if you have any questions, ask me. You know, I just sent an announcement about it. So if you have more questions, you know. Okay. So if anyone didn't do the attendance, just let me know right now, I guess. I have this. Yes. Yes. Or like eraser, so if you want to erase something. So I'm going to give you a scan run. And sometimes the students just like cross out with like trends, but my software doesn't read that. So sometimes I try to catch it. It's just easier to erase it when you have like yes. I'll give you a unit.
Thanks. Let me make a question. Have a good day.
You too.
Is there gonna be
Institutional isomers or isomers. They are the same. This is the first type of isomers that we studied. And they have the same chemical formulas. But they have different arrangements of atoms. Different arrangements of atoms. And just like on a side note, I remembered in one of the slides that I had, or like several of the slides that I uploaded, which was the book, the publisher's slides, by the way. It was writing like interconvertible, and then it spelled that like ABLE. And when I was typing that on Canvas, it was giving me an error, and I realized it's like IBLE. So it was kind of interesting to me that the book had like typos, you know, because I'm like non-native English speaker, so sometimes, you know, if I don't know how to spell interconvertible, I just see the book spelling and then I think that, okay, this is the right one. So excuse me for not catching that, also your publisher. Anyway, so that was like a comment side note, but for like constitutional and structural isomers. So we have the same chemical formula, but different arrangements of atoms or pattern or different bonding pattern. Meaning that consider methyl butyrate and propyl acetate. And I think it's kind of like goes without saying, but I don't expect you to know, for instance, how to write methyl butyrate, you know, or like propyl acetate. I only asked you the things that I covered in the class. So for naming compounds, I asked you IUPAC naming of alkanes and cycloalkanes. Is that clear? Those ones I expect you to know how to write their structure if you have the formula, or how to write the formula if you have the structures. But for these ones, if I ask questions about isomers and you don't know how to write the IUPAC name, I'm just going to give you the formula or like structures, you know, or like you saw in your homeworks or quizzes, how I asked true or false questions, or like which of the following is correct, is not correct, which brings me to this point that pay attention in the exam. You know, lots of the times the students come to me and they say, I answered the question right. It was saying this answer is correct. And I tell them, yes, but I asked you which one is not correct, right? So first of all, pay attention to that. Sometimes I capitalize not, N-O-T. Sometimes I forget. So you should read the question carefully regardless. The other thing, and this is like for your life, any multiple choice question that you take, even if you're 100% sure you know the answer, read all the options. And sometimes you answer, you know, I say which of the following is not correct, you think is correct, and then you read the first one and it's correct, And then you read the second one, it's also correct. And you're like, what's happening here? And then you read the question again, you realize you were asked for the wrong answer. Does that make sense? Because I have lots of students that they know the materials, they are like really top students, but they do bad on the test because they simply didn't pay attention, okay? Anyway, so methyl butyrate is like C5H10O2. Propyl acetate is C5H10O2. So just by looking at the chemical formulas, you think these two substances are the same, right? You cannot distinguish them. But when I write the chemical structures for them, one of them, which is like methyl butyrate, is like CH3, CH2, CH2, and then we have like this double bond here for oxygen, OCH3. Okay, and for propyl acetate, we have the structure as following: CH3, and then we have like a C double bond O here, then oxygen, carbon, hydrogen, hydrogen, carbon, hydrogen, hydrogen, carbon, CH3. You see the difference here? We have like one, CCOC, kind of like here, and then here we have like carbon, carbon, oxygen. So here, I guess better way to say this, we have like CH3 here, we have CH3 here too, but this carbon is attached to oxygen here, but here this carbon is attached to a carbon here. Can you all see the difference between the two structures? So if I don't write the structure and denote that here we have CC, here we have CO, and just give you the chemical formula, you don't know that these are different. So these are constitutional or structural isomers. But for the other categories, remember, here if carbon is attached to carbon, in the constitutional, carbon is attached to oxygen. You see that bonding pattern is different,